Hi, my name is Josh Moore. I'm the Senior Product Portfolio Manager here at Solidworks for the Solidworks PCB products and technologies. In this presentation, we'll talk about the rise and now falling of traditional design silos and how that's impacting the industry and our customers. Throughout the presentation, we'll talk about the division of design tasks. We'll talk about the changes that are affecting the design silos and the people within them. And then we'll finish up by talking about product creation, the change and evolution of products and technologies to get a product out to market. So let's take a look at a typical engineering group. This is the kind of engineering group that we have all grown up with throughout our careers and has been this way for a long, long time. We have the classic electrical engineer whose job it is to define the circuit and define the logic and capture the circuit definition. The layout engineer or the layout specialist whose job it is to do the physical place and route. We have supporting engineers for doing signal integrity and signal quality analysis, FPGA designers, analog designers, and component engineers. Now for somebody like the component engineer, if you remember back in the day, it was his job to actually go to a bookshelf to look for component information. Prior to the internet, it was not possible to go online or to access a database to find component information. You actually had to go to a book from a manufacturer, thumb through the book and find the appropriate information that was needed by the electrical engineer, and then provide that information to the electrical engineer or the procurement person who was going to buy those particular products. Now in this particular example, everybody has their own specific roles and responsibilities within the engineering organization. The electrical engineer typically did not do place and route. The layout designer didn't do SI work. The analog designer was specific to his task, and so on. As the performance and capability have evolved exponentially for electronic products, those divisions of tasks and design silos have become more ingrained in the engineering organizations. Take, for example, something like the car stereo. In this example, circa 1960, 1970, a very simple basic car stereo. It played music, it had some tone and volume controls, had a couple of wires for speakers, and its design was relatively straightforward, has about a dozen or so transistors and logic devices to make it do what it did. Play music, that was about it. Fast forward into the 80s and 90s, and the car stereo is getting a little more complex, a little more complicated. You now have a CD player, you have a digital display, you might have a graphic equalizer, surround sound, and the design is getting a little bit more complex. So no longer is it just simple transistors. Now you've got devices that do more than one function. You've got a lot more system in this particular electronic device, and the design challenges are increasing appropriately with this evolution of the car stereo. Now take, for example, the modern infotainment system. Yes, in this picture there is indeed a car stereo. It's hard to find. But the modern infotainment system is really a system of systems. So now the design and complexities further reinforce the division of design tasks within the engineering organizations. As the complexities and challenges have gotten that much harder, the products and the knowledge for the particular domains, whether it be electronics design, PCB place and route, signal and quality, analog design, have really reinforced the division of design tasks for something like this modern infotainment system, which everybody now has specific challenges related to their particular job. As performance and capability continue to evolve, so too do the design and technological complexities of printed circuit board and electronics design. This is true across every industry, from telecommunications to military and aerospace, medical and transportation. More and more high-speed nets are becoming the norm on printed circuit boards. Where many years ago you might have had a few nets on the board that needed to be constrained and managed, now almost every net on the board needs to be constrained and managed in some way. Higher pin count devices are also the norm. More and more functionality is being placed on silicon in these devices, resulting in higher pin counts for flat packs and BGAs. Smaller geometries are also becoming the norm as an effect of this. The larger the flat packs get, the larger the BGAs get, the smaller the pin pitches tend to get. The BGA ball size continued to shrink as well. This results in increasing densities. So not only can I put more and more functionality into these larger chips, I can put them on both sides of the board. The discretes themselves are becoming so small they're hard to see with the naked eye, meaning in the same space as a through-hole resistor, I can now have so many more discrete devices than I could with that through-hole. Complex constraints are also the norm. Not only complex constraints themselves, but constraints on top of constraints on top of constraints. Many years ago, again, it was just a few nets on the board that needed to be constrained and managed. Now it's almost every net on the board that needs to be constrained and managed. New standards and compliance rules are now also commonplace. A few years ago, the government stepped in and said no more lead in the PCB process, PCB design. So a lot of parts instantly became obsolete. There was a change in the manufacturing process that supported a more eco-friendly manufacturing and fabrication. Now let's take a look at business and market challenges. For every product, there's control, there's some kind of electronics, there's a mechanical aspect, a computing aspect. While the electronics part remains relatively the same for any given electronic device, for a mechatronics type device, the mechanical aspects become more and more critical. Take this drone, for example. Changing the mechanical aspect of this drone would hinder its ability to fly. You can't just simply make it any shape and size that you want to make it. Unlike other electronic devices that would still continue to function, this drone would no longer fly, regardless of the electronics, the control, and the computing within it. The other challenges that we face is an ever-increasing demand for higher quality, for lower cost, be it product cost, labor cost, the ever-shrinking product and project schedules that everybody has to deal with, and the ever-present competition that's going to come along and do it faster, cheaper, smarter, or whatever the case may be. Now, giving all these changes and complexities and evolution of technologies, business and market challenges, the products that we use, the products that are designed for the individuals within their area of roles and responsibilities have also had to adapt. The electrical engineer, for example, needs schematic tools that are far more capable and productive than just a few years ago. Component data management built into schematic tools has become the norm. Design and data management across an entire engineering organization has become the norm. Constraint-driven layout, 3D design and visualization, and high-speed design are all fairly recent enhancements in electronics design and printed circuit board design tools. Now let's take a look at the individual silos and the walls between them in our engineering organization. On one side of the wall, you have the various engineers who are responsible for logical circuit design. And this could be schematic design itself, signal integrity, analog design, component research, whatever the case may be. Then you've got another silo group of people, the layout engineers, the PCB design specialists, who are responsible for physical design. And then on the other side, you've got mechanical engineers that are responsible for the enclosures and the assembly design. And for the most part, these organizations have been siloed from each other. We had the saying, we threw information over the wall for somebody else to receive it. This is largely the way that we all grew up with engineering organizations and everybody having their individual roles and responsibilities. And as things have gotten more and more complex, the need for everybody to stay in their individual roles and responsibility areas has become more and more critical. Back in the day, you would not have found an electronic engineer who was doing PCB layout, or a PCB layout specialist who was doing SI work, or a mechanical engineer that was involved in the ECAD or electronics engineering process. So now let's take a look at the changes that are affecting these design silos. The change of demographics, technological and technology commoditization, and systems of systems. So as we saw before, this is how our typical engineering organization looked. There was a high degree of specialization for the individuals in each of these areas, dealing with their roles and responsibilities. There was a high emphasis on tools and expertise. Silo domains and very limited interactions was more or less the norm. And in general, across the market, you found complexities at the high end of the market and simplicity at the low end of the market. One of the things that's changing is now we have this concept of the do-it-all engineer, or cross-discipline domain experts who can do more than just what their predecessor did in his or her area of responsibility. So electrical engineers are now outfitted with tools and domain knowledge for doing signal integrity work. Layout designers can be component engineers. Analog designers are, for the most part, no longer in existence, although there's still some pure analog in portions, in some segments of electronics design. But for the most part, the analog designer has been replaced by a digital equivalent of some kind. The component engineer no longer has to go to the bookshelf. The electrical engineer can now go to the web for an online component vendor. Layout designers can go online for libraries of 3D models and component footprints. The other thing that's changing is nobody really goes to school anymore to be a printed circuit board designer. You now have students that are graduating with electrical engineering degrees or mechatronic engineering degrees that are filling the classic PCB designer role. So this is a copy of this month's Printed Circuit Board Design and Fab magazine. The headline is, "The countdown is on. The 50% of designers who consider themselves PCB layout specialists see retirements in 10 years. So where this started was PCB Magazine started an annual survey a little over 15 years ago. And one of the things that they asked, in addition to design types, design challenges, design profiles, salaries that people were making, was also their age. Now, as time went on, there was a 10-year anniversary of this particular annual survey. And when that survey came out, one of the findings that surprised everybody was that everybody got 10 years older. And the question was, where's all the young blood that is replacing everybody as they get older and retire or move on? To just reinforce this fact, this is the part of the survey from September 2015. There were approximately 600 respondents. When asked about their age, a full 72% of everybody who identified themselves as PCB specialists turned out to be over the age of 45. Now, what this essentially means is the PCB layout specialist who's been in the industry for 20 or 30 years or more is retiring, or they're moving on. But they're not being replaced by pure PCB specialists anymore. They're largely being replaced by engineering students or mechatronics students who are coming out of college and who don't know specifically PCB. They know a little bit about electrical engineering, know a little bit about signal integrity work, analog design, component engineering, and in some cases PCB. The other thing that's changing in the industry right now is the big disruptors. We've had big disruptors from time to time over the last couple of decades. The most current one is this Rise of Mechatronics and IoT, Internet of Things. Yes, I will use that term fairly loosely because IoT means a lot of things to a lot of people and is different depending on who you ask. But for the most part, take the picture down in the bottom right with the connected robot. In this particular mechatronics design, there's mechanical aspects, there's electronics design, there's data management, connectivity to the cloud, simulation, various forms of mechanical fabrication. This is a classic mechatronics design. The picture on the left is a collection of everyday objects. Now, what makes this picture particularly unique is that none of the objects in this picture is brand new. The washer and dryer has been around for almost 100 years. The doorknob has been around for over 1,000 years. But somebody decided that they were going to take these devices and make them smart. And oh, by the way, make a business or make money along the way. So one of the things that's really driving the rise of mechatronics, this innovation of IoT, this ability to take everyday objects and make them smart or connected, is really an electronics design revolution happening in the industry right now. For the most part, we really don't design at the gate level anymore or at the logic level. We design at the system level. Think back to the infotainment system in the earlier picture, where it's just essentially a system of systems that is engineered together to create one larger system. There are reference designs available to engineers. So no longer do you have to design a lot of complex pieces of your design from scratch. You can get reference designs that are essentially plug and play or design into your design to make it whatever you want to make it. For example, the picture at the bottom left was a quick search on the TI website for a power supply. Not only did I get the schematic for the power supply, the design guidelines for the power supply, but also the design files and the output and manufacturing files. And it wasn't just for a TI regulator, it was for an actual proper power supply that all I had to do then was engineer it to make sure that the ins and outs and the load that I was applying to it were acceptable for my particular requirements, and I had a full-blown power supply. Take, for example, the advent of Arduino and embedded computing devices. That kind of commoditization means that if I have an idea, whether I'm a hobbyist, an engineer, an entrepreneur, a 12-year-old kid, as in this picture right here, if I have an idea, I can use an Arduino or another embedded computing device or platform as the basis for my idea. Specifically for the kid in the picture, he's a 12-year-old kid who's designing smart connected projects at his school, his middle school. And when they're done creating the smart connected products, they're going to manufacture them in their fab lab that they have at their school. And the commoditization isn't just limited to whole systems of systems. If I need DDR4, for example, or if I need certain memory components, I can grab those as reference designs from companies like Qualcomm or MediaTek or Huawei. And as we saw before, once again, the tools have had to respond to this change in demographics, this change in design requirements, this change in product capabilities that really cover everybody from the classic electrical engineer, the do-it-all engineer, the mechatronics designer, all the way to somebody who's a hobbyist or an entrepreneur, or in the case of the 12-year-old, a 12-year-old kid with no formal training. So tools now have to support design-in kits, concurrency, mechatronics design. Tools need to be formed around a unified design environment, have integrated flows, advanced automation, and virtual prototyping. So let's go back and look at our walled silos that we've become accustomed to. So this is where things are really starting to change. No longer is there a physical wall and barrier between logical circuit design and physical circuit design. You now have an integrated platform for whomever is doing the electronics design, and more cases you now have a do-it-all engineer or a mechatronics designer who's responsible for both the electronics design and the physical representation of that electronics design. So now let's take a look at getting products created, or product creation, and the effect it has on mechanical engineering and electrical engineering, and why these really need to be a two-way street heading into the future. So if you take a look around at every electronic device that you can see, you will see no printed circuit boards. You don't go to the store and buy a printed circuit board. It's not a whole lot of fun to play with. You can't watch TV on it. It doesn't play music. It certainly wouldn't fly. Every electronic device that you can see or that you can buy is inside a mechanical enclosure. In a lot of cases, the mechanical enclosure is there merely for the protection of the electronics inside to give the human something to hold on to. But in the case of mechatronics, it's an integral part of whatever that device happens to be. Going back to the drone in this case, the drone shape of this mechanical part can't be different. If it was a square brick, it wouldn't fly. It needs to be aerodynamic, it needs to be streamlined, it needs to be appropriate for the mechatronics device that it is. So this brings the need for electromechanical co-design, because at the end of the day, product creation is more than just schematic to Gerber. And what I mean by that is, as in that previous slide, every electronic device is a combination of the electronics and some kind of mechanical enclosure to either protect it, give us something to hold on to, or in the case of mechatronics, actually make it perform as it's intended to perform. But there's a fundamental challenge with bringing the mechanical worlds and the electronic worlds together. Yes, they're generally separated by a wall. We pass data over that wall or throw data over that wall in the form of DXF, IDX, STEP, or whatever the case may be. But more fundamentally than that, these two worlds are alien to each other. They don't speak the same language. They don't have the same set of data. The concepts and the engineering practices are very foreign to each other. Working here at Solidworks with a combination of electrical people and mechanical people, it's even hard to have a conversation with those people, between those people, because they speak a different language. Mechanical guys are talking about faces and mates, and electronics guys are talking about layers and traces and spaces. So how do we get these two worlds that are so foreign to each other connected intelligently to drive the business of the future? Well, once again, this is where products and technologies have had to step up to address the needs of the market, changing demographics, change in business drivers and business requirements. ECAD, MCAD co-design has become more and more critical to business and product creation success. No longer can it be the ECAD guys design their product, the mechanical guys design their product, and then somewhere along the way they bring it all together to make sure it fits. Cross-discipline flow, mechatronics design, further integrated flows have all become now the norm, especially with SolidWorks products, SolidWorks PCB and SolidWorks mechanical CAD tools. ECAD, MCAD ECOs, an ecosystem of product creation capabilities that go far beyond simple electronic creation, mechanical creation. There's also the need for simulation, electronics cooling, cable and wiring harness, and collaboration services. So this brings us again to our silos and how we're breaking down the barriers between these silos. So we've already seen as we've broken down the barriers on the electronic side between logical circuit design and physical design. Now we're breaking down the barriers between the ECAD world and the MCAD world. So instead of talking about logical design, physical design, mechanical design, we're really now talking about product creation and bringing all these engineering organizations together, bringing all the different disciplines together such that we're creating products in the most intelligent, seamless way possible. Now that we've broken down the barriers between the electronics world and the mechanical world, we can start to realize more time saved, more money saved. We can start to realize an improvement in accuracy between our electronics and our mechanical. There's less time and effort involved, where in some cases, engineering organizations start by collaborating at the beginning of a product design cycle, do nothing in between, and then come back together and collaborate at the end, hoping that everything fits together correctly. Bringing the electronics world and the mechanical world together reduces errors, allows us to communicate better, and overall produce better quality products.